On this video, I'm going to do a pretty involved problem working through some phase changes and the heat required for changing those phases, and then the heat required just to take a substance and change its temperature. So we're going to be working with a couple different equations. So it says, how much heat is needed to change 25 kilograms of negative 8 degrees Celsius ice to 25 grams of 100 degrees Celsius steam? And then I give you that the latent heat of fusion for water is 80 calories per gram. The latent heat of vaporization is 540 calories per gram. And the specific heat of water is 1 calorie per gram degree Celsius. So we have quite a few different things going on here. Notice that we are starting with 25 kilograms of ice that's at negative 8 degrees Celsius. So our ice is not going to immediately start to melt because our melting point isn't until 0 degrees Celsius. So first thing that we're going to end up doing is we have to warm the ice. Once we get the ice up to 0 degrees Celsius, okay, so let me write the temperatures here, negative 8 to 0. Once we get it up to 0 degrees Celsius, then we will enter that phase change for melting the ice. Now, as we are melting the ice, remember, during a phase change, the temperature does not change, so it's going to be at a constant 0 degrees Celsius. Once we get all that ice melted, then we'll have liquid water, and that liquid water will be at 0 degrees Celsius, so we then have to warm the water. So from 0 degrees Celsius up until we get to 100 degrees Celsius, because at 100 degrees Celsius is where we will start vaporizing our water. It'll start to boil. And then that'll take us into another phase change where our temperature doesn't change, stays at 100 degrees Celsius until all that water is vaporized, which will then lead us to that 100 degrees Celsius steam. So we're going to have 4 different components of this problem that we're going to have to work through. So on this first section here, when we are just warming up the ice, we are going to be using the formula. Sorry about that. I don't know why it does that sometimes. Give me just a second. There. So we're going to be using the formula Q is equal to mc delta T. So Q is the heat that we are computing. M is the mass, C is the specific heat of the substance, and delta T is the change in temperature. Now, before you just start throwing numbers into this, you always have to make sure you pay attention to the units that you're given. Now, in this particular example, our heat of fusion, heat of vaporization, and specific heat of the water are all given in calories per gram. Okay, we have grams in there. So the first thing that we have to do before we even start working with this equation is we have to make sure we change our kilogram unit here into grams. So 25 kilograms is really 25,000 grams. If we don't do that, our units are not going to cancel out the way that they need to, and we will not end up with the correct answer at each step. So now, the mass of our substance is 25,000 grams. Okay, the specific heat. Now, we are using just the regular specific heat of water because we are not in a phase change. When we get into melting, we will use the heat of fusion, and when we are boiling, we'll use the heat of vaporization. So we just have to use the specific heat of water, which is 1 calorie per gram degree Celsius. Okay, and then our delta T here, that's the change in temperature. So we have to go from negative 8 degrees up to 0 degrees. So we're going to have a change in temperature of 8 degrees Celsius. Now, if you notice, when I multiply this out, I have a grams label in the numerator and a grams label in the denominator, so those will cancel out. I have a Celsius degree in the numerator and a Celsius degree label, in the denominator. They will cancel out. and the only unit that we're left with is calorie. So when we are doing this particular computation, our heat is going to be measured in calories for this one. So you always want to make sure that you pay attention to your labels. Once I make sure that my labels all work out, I go ahead and just multiply that all together, and I got, let's see, 200,000 calories. And that is just to change the, not to change the ice, excuse me, to warm up the ice from -8 to 0 degrees Celsius. So that's just one component of our process. Now, when we jump into this next step, where we go into melt the ice, we are not in the same situation as what we were up here. We are now in a phase change. So when we are in a phase change, our formula changes slightly. And one way to think about it is during a phase change, there is no temperature change. So if we were to use this same formula up here, our delta T would be 0. And anytime we multiply by 0, our product is 0. So this formula, if we try to use this formula during a phase change, it will always produce 0 heat, and that can't be the case. So if you're struggling on when you should use each formula, kind of keep that in mind. For a phase change, our formula is still similar. It's Q is equal to M times L. So Q still represents the amount of heat energy. M is still the mass, but L is now either your latent heat of fusion or your latent heat of vaporization, depending on which phase change you are in. Well, since we are melting, we're going to be using the latent heat of fusion. Now, again, our mass is still 25,000 grams. And our latent heat of fusion for water is 80 calories per gram. Okay. And that will give us Q. Now again, I need to check my units. So I have grams in the numerator and grams in the denominator. They will cancel each other out, which is good. It leaves me with just calories. So when I take 25,000 times that by 80, I should get 2 million, I believe. Okay, and again, my label left is calories. So that's a good sign. So far we have calories and calories. Our units are working out nicely. Okay, so once we get through melting the ice, now we're going to start with water that's at 0 degrees Celsius. It's going to be very cold. And then we have to warm that water clear up to 100 degrees Celsius so that we can get it to its next phase change. But we have to put in heat energy in order to do that. So now we're going back to our first equation here. Our mass is still 25,000. Okay, our specific heat is still 1 gram, gosh darn it, 1 calorie per gram degree Celsius. I'm trying to use the same colors here. There we go. And now our change in temperature, so our delta T, we're going from 0 to 100 degrees, so that is a change in temperature of 100 degrees Celsius. Okay, check my units, so grams in the numerator, grams in the denominator, Celsius in the denominator, Celsius in the numerator, and again, it just leaves me with calories. So I can go ahead and multiply that all together. That got a little ugly there. My unit would still be calories. Oh shoot, that was supposed to be black. Oh well. Okay, and so to change from 0 to 100 degrees Celsius, I have 2,500,000 calories. Now the last thing I need to do, because remember I need to get this clear up to 100 degrees Celsius steam, so I need it all to be vaporized, I need to take it through the boiling phase, all of it through the boiling phase. Now again, we are at a phase change, so our temperature is not going to be any different than what it was before. So I'm going to be using the same formula that I had in part B here when I was melting it. So I'm going to have Q is equal to, here's my mass, 25,000 grams. And now, since I'm vaporizing it this time, I need to use the latent heat of vaporization from the text up here, which is 540 calories per gram. Okay, check my labels. My grams cancel out with each other. Multiply those two together. I get 1, 3, 5. Okay, so 13,500,000 calories. Now the last thing I need to do is I need to add all these up, because this is just telling me how many calories it took to do each of the steps, and the question is asking for how much heat is needed to change it from that -8°C ice to 100 degrees steam, 100 degree Celsius steam. So I need to add all these up. Okay, if I ended up entering them into my calculator correctly, I got 18,200,000 calories. Now I need to go back and check my significant figures. So my significant figures, let's see, I have 25 grams, that is a measured value. These latent heat of fusion, vaporization, and specific heat, those are all given standard values. Let's see, I only have one significant figure from my -8 to my and one in my 100. So I only get one significant figure, it looks like. So I would actually want to round this to one significant figure. The 8 would bump it up. So if we're going with significant figures, I would need 20 million calories. Now, most of the questions that you will have will not be all of these steps at once. It will probably be either one step or two steps at the most. But I wanted to do kind of, the bigger problem so you could see each individual component and how they all would technically work together. But most of them that you will have will only be maybe part A, or will only be A and B type of a deal. So most of the time you won't have 4 components, or we could have even gone higher to 5 components if we needed to increase the temperature of the steam. So this problem was a bit bigger than what you will probably have, but at least it did show all the different pieces.